In this video, we're going to take a look at some of the physical applications we can use calculus for. So a quick review of some physics, because these are physical applications, we need to know the physics behind them. Mass is density times volume, units are generally in kilograms. Work is equal to the force times the distance, our unit is joules. We use Hooke's law, which is dealing with springs, and that's F equals kx, where k is the spring constant and x is the displacement. We also have that force equals density times gravity times volume, in case we want to be lifting something or moving something. Rho, Greek letter, is equal to density. The density of water is 1,000 kilograms per meter cubed, and g is the acceleration due to gravity, which is 9.8 meters per second squared. So if we want to find mass, we said mass is density times volume. We can also use calculus to do that. So mass is the integral from a to b of the density function dx. So if I want to find the mass of a thin bar that has a density function rho of x equals 1 plus x squared with a length going from 0 to 2, I can say that my mass, lost my pen, the mass is equal to the integral from 0 to 2 of 1 plus x squared dx. So then I'm just integrating. So this is x plus 1/3 x to the third from 0 to 2. So this would be 2 plus 8/3 minus 0, which is 14/3. And my units here would be kilograms because I'm dealing with mass. Hooke's law is talking about a spring. So if I have something anchored to a wall and I have a spring here, if I stretch my spring, there's work that has to be done to do that. Likewise, if I have to squeeze the spring and compress it, work has to be done. So to find out that work, I have to use my constant of proportionality, my constant for the spring, times my displacement. So the first thing we have to do, if we're going to do a problem like this, is we need to know what is that spring constant. So if we have a force of 30 newtons to stretch and hold a spring 0.2 meters from its equilibrium position, the first thing I need to do is figure out what is that spring constant. So I'm using f of x equals kx. My force, I was told, is 30 newtons. And that's when the displacement is 0.2 meters. So solving for k, I get my constant is 150. So now using that 150 for our k, we can rewrite this formula as f of x equals 150 times x. And we want to find how much work is required to compress the spring 0.4 meters from its equilibrium. So the amount of work needed is the integral. So I'm starting at equilibrium 0 and I'm compressing it, which makes I'm shrinking it. So I'm actually going to negative 0.4 and I'm integrating 150x dx. So this is 150 times 1/2 x squared, evaluated from 0 to negative 0.4. So I have 75 times negative 0.4 squared is 0.16 positive minus 0. And multiplying this is equal to 12 joules. So my unit for work is joules. So 12 joules of work. Now if I was stretching the spring, this would become a positive 4, and I would still get the same value for this function. The other type of work problem we like to deal with is lifting. So if I have a tank and it's filled with water, so this red cylinder is the level of my water, and I'm trying to push the water all the way up, so maybe there's a pipe in here, and I have to get it all the way up here and out, the formula to find that work is the integral from where I'm starting to the height I'm going. Rho is the density of what I'm lifting, so the liquid, g is gravity, times the volume of what I'm lifting times its distance. So remember, the area of my slice times the height that I'm going will give me my volume times that change in distance. All right, let's try one of these. So we have a tank in the shape of an inverted cone, has a height of 15 meters and a base radius of 4 meters. It's filled with water to a depth of 12 meters. We want to determine the amount of work needed to pump all of the water to the top of the tank. Assume that the density of water is 1,000 kilograms per meter cubed. Well, so this is the integral from rho times gravity times the volume times the distance. Well, they said this is an inverted cone, so the volume of a cone is 1/3 pi r squared h. Now we have to be a little careful here because I have two variables r and h, and I can't have both of them when I plug it into the integral. So I have to remember when I'm dealing with a cone, I have similar triangles. So the actual base radius is 4, the maximum height is 15, and that's in proportion to my radius and my height throughout the whole problem. So solving in terms of h, because h is my height, r is going to equal 4h divided by 15. So I'm going to change my volume. So now I'm ready to do my integral. So the work equals, I'm raising all of the water, so it's starting at the bottom 0, and it's going to the top 15 feet. Rho and g are constants, so I'm just going to leave those for right now. I'll plug those back in at the end. The volume is 1/3 pi. Instead of r, I have to put it in terms of h, so 4h over 15 squared h dh as my height changes. So I'm going to pull out my constants. So I have pi rho g over 3, the integral from 0 to 15. This will be 16 over 225 h cubed dh. Again, pulling out my constant. So now I have 16 pi rho g over 625. And then my integral, this becomes 1/4 h to the 4th, evaluated from 0 to 15. So when I plug these in, so I'll have 300 pi rho g, and then I'm just plugging in. So my work here, when I plug this in, is 300 pi. Rho, density of water, is 1,000. Gravity is 9.8. And so in terms of pi, this is 2,940,000 pi joules. So a lot of work to push up that amount of water.